Science, Medicine, and Technology Subcommittee of the Curriculum Committee of HATS. It is my pleasure to be here. I'm glad to see we have so many folks. It is certainly a relevant topic. It is amazing how many things we take for granted. And that the lights go on when we flip the switch is high on that list. But simply because we're used to getting things the way we have been, we know that sustainability continues to be an issue. It's certainly an ongoing focus for us on our committee as we seek to give perhaps a broader perspective than what we might be aware of as we live our daily lives. And so for that reason, I'm delighted that Jeff Christians is willing to bring us such a perspective. He earned his PhD in engineering from the University of Notre Dame in South Bend, Indiana. He spent 3 years working as a scientist at the National Renewable Energy Laboratory. He has been teaching at the engineering department at Hope College since 2018. He's got a few students with him that I will allow him to introduce. And without further ado, here's Jeff.
All right, thank you very much, Bruce. Appreciate the introduction. And yeah, thank you all for coming here to join us this morning. This is great. I'm excited to have so many people. So as Bruce said, I'm going to talk to you today about, here, if we can get my presentation working at least. Right, it's not a presentation online without technical difficulties. All right, there we should be good. So yeah, as Bruce said, we're going to talk, myself and two of my students are going to talk about energy today. I first like to introduce Liz and Josie, who will be joining me. You'll hear from them a little bit later. Both Liz and Josie are rising juniors at Hope. Liz is a major in mechanical engineering. Josie is a major in chemical engineering, and they've been gracious enough to help me put together some of the information for this presentation, as well as help me present today. So you'll hear from them both a little bit later today. But yeah, as Bruce said, one of the things that's interesting about energy and different than some other things, right, is for the end user, you plug something in and you turn the lights on. So it doesn't really affect you directly what's happening behind the scenes. But I hope we can convince you that what's happening behind the scenes is both important and is changing incredibly rapidly. So I think that's one of the takeaways from this talk today. Hopefully we'll be able to show you some things that there are a lot of positive changes, but more needs to happen. But kind of the prospects for energy and the future of energy is changing incredibly rapidly. So we wanted to start, one of the things that I'm interested in as an engineer is contributing to help humanity solve challenges that we face together. So Dr. Richard Smalley, who is a Nobel laureate and Hope College's claim to fame, he actually attended Hope for 2 years as like a 2 and 3 program, and then taught for most of his career at Rice University in Houston. So he was a Nobel laureate in chemistry. And in 2005, he gave this really impactful talk called the Terawatt Challenge. And basically he laid out the challenge that we face with energy. And I think a really good way to visualize this, he kind of split it up. What are the biggest challenges that humanity faces? Population, democracy, education, disease, we're obviously facing that right now, terrorism and war, poverty, environment, food security, water security. So he kind of named all of these things and put them in this type of hierarchy, right? Food and water are some of the most important, but actually he named energy as the most important of humanity's grand challenges that we're going to be facing over the next, say, 50 to 100 years. And the reason, and Josie will talk about this a little bit more closely in a bit, but the reason that he put energy at the top of this list, or in my list, I guess at the bottom, But the reason that energy was number one is because access to clean, renewable, inexpensive energy, inexpensive is probably one of the most important parts, but access to inexpensive energy helps helps us combat all of those other things like water security and food security and disease and education. Energy is a component. It's not the only component. All of these problems are really challenging and really big, but it is one component that helps and is necessary for all of these other problems. So let's talk a little bit about world energy use. So world energy use has been rising. That's probably no surprise. It's predicted to continue to rise as population increases. It's predicted to rise about 28%. This is predictions from companies from the US Energy Information Administration and ExxonMobil, places like that. And it's predicted to rise primarily in the developing world. So you can see here the OECD, which the US and many European nations, as well as some South American nations, are members of the OECD. Our energy use in the OECD is predicted to actually maybe decrease a little bit due to gains in energy efficiency. Right, things like Energy Star appliances and better air conditioning units, better lighting systems, those kind of things are improving our energy efficiency, so we're actually going to be using less, but the developing world is going to be using more. They're going to also see gains from energy efficiency, as you can see in the top, but their net demand is going to be increasing. If we zoom back a little bit and look at the history of our energy use here in the United States, we're going to be talking a lot about the US, although a lot of the things that we'll talk about are relevant globally. If you look at energy use in the US, obviously, right, this is since 1776, which is one of the reasons why I like this. Right, if you go back to early days in the US, we used quite a bit of energy per person, but most all of it, really all of it, was wood for heating. The Industrial Revolution obviously started us using coal. You can see that black line coming up around 1860 when we started using coal. And then you can see certainly in the last few years on the side of this graph, after 2000, now there are a whole bunch of different lines. So really the story of energy use in the United States and the world has been a shift from really a single source, wood, to maybe two sources, wood and coal, to now a whole ton of different energy sources. So it's really become very diversified in terms of where we get our energy. We can look, I think this is maybe a little bit more clear. A lot of this is the same information as that last graph, but this shows simply the last few years in the US since 1950. So each color is a different type of energy. And you can see in the US, our energy use in all sources was going up. Really since 1950, obviously we can trace that back all the way to 1776 and before that. Energy use in the US had been going up, been going up, been going up. About 2005, that changed. So you can see there right about 2005, we actually have a plateau in energy use here in the United States. So since 2005, we have not been using significantly more energy. And that's because of energy efficiency gains. So 2005 is when the US really started to push things like Energy Star appliances and LEED certified buildings and LED lighting. So that those kind of technologies have really helped us to kind of flatten our energy use. You can see it's obviously not going down. We're still using the same amount of energy, but it's not continuing to go up. There's definitely a change in slope. If you look at where our energy is coming from, not just the total shape of the graph, but if you look down here at the bottom, you can see this brown section here. That's coal. So we hear a lot in the news today about the coal industry and how the coal industry is shrinking. That's definitely borne out in the data. So you can see starting about 2005, 2004, coal has shrunk by almost 50%, maybe 40%, since 2005. And we'll get into some of the reasons for why that's happening a little bit later with some of the actual numbers, but you can see there's basically a really sharp decrease in how much coal we're using. So our total amount of energy is flat. So what's actually making up for that? Well, we're predominantly replacing coal here in the US with natural gas. So natural gas is this blue here. So you can see since 1950, that's been kind of steadily increasing how much natural gas we're using. But here again, around 2005, then that started to increase much more rapidly. And that kind of, we've been displacing a lot of coal with now natural gas. Right, you hear, again, in the news, you hear about, we hear about these things all the time. We hear about fracking and developments in fracking and natural gas extraction. So that's really, again, we'll get into some of the economics of why this shift from coal to natural gas is happening a little bit later, but just to kind of paint that picture. The other thing that's happening is, it's a little harder to see, but this green here is renewables. If you go back to 1950, 1960, basically all of that is hydroelectric power. And in the present day, it's a mix now of hydroelectric dams. It's a mix of wind turbines on the Great Plains, and it's a mix of solar power. And we'll talk a little bit about what's happening in all of those different spaces too. But I like this because it gives a picture of really kind of the general mix of what's happening in the US. If we look at last year, I think this gives a picture of kind of the big changes that are happening in energy. So this is US energy in 2019. On the right here are energy production facilities, power plants that have retired, have been decommissioned. So you can see the black dots here. The size of the dot is the size of the power station. So this one here, the Navajo power station, was a 2.3 gigawatt coal power plant. That's a very big, we're gonna be talking a lot about gigawatts and megawatts. The Holland power plant, which we'll talk about here in a little bit, the Holland power plant is about 1.5 or 150 megawatts. So this Navajo station is over 10 times as large as the Holland power plant. Right? The Holland power plant can supply basically all of our electricity for the whole city of Holland. So this can supply maybe 300,000 homes. You know, that kind of an amount of people. So it's a very big power plant. So we're seeing predominantly the retirement of coal power plants, as we kind of saw borne out in that last graph. We're also seeing some decommissioning of nuclear power plants, and some, not very much, but some decommissioning of natural gas power plants. But you can see basically in the retirement section, we're retiring large scale energy production. And then over here on the left, we're replacing it with lots and lots of small scale stuff. So you can see all of the dots on the left pretty much are small. All of the dots on the right are big. So we're actually adding more energy than we are taking off the grid, but most of that is wind, about 46%. So about half of the new capacity that we're putting on the grid is wind. And then the rest is split between natural gas and solar. So maybe it will surprise you to learn that really about 2/3 of the new generation that we're putting onto our grid today is renewable. Only about 1/3 is actually kind of traditional fossil fuel, and all of that is natural gas. We're not building any new coal anywhere in the United States. Whenever I talk about energy, I hear a lot about nuclear reactors and nuclear power. And I think this is a graph that I like to see, that I like because I think it tells kind of an interesting and complicated story. So nuclear reactors, since Enrico Fermi invented the first one in a tennis court in Chicago, during the Manhattan Project, right? So back here, and after World War II, nuclear power was hailed as the future of energy. This was going to be drive down energy prices so that it was too cheap to meter. And countries around the world, including the US, including the European countries, started building lots of nuclear reactors. And you can see that, right? We see this pretty dramatic increase in nuclear reactors worldwide. And then right here, right about 1986, the amount of nuclear reactors worldwide stagnated. Does anybody, if anybody can unmute themselves, does anybody know what happened in 1986 that might have caused the nuclear reactors to stagnate?
3 Mile Island.
Chernobyl. That's a good guess. That was a little earlier.
Chernobyl.
Chernobyl, right? So in April of 1986, that was the Chernobyl disaster. So I like to see, it's surprising to me how quickly that changed worldwide opinion of nuclear power. And so the Chernobyl disaster, obviously the meltdown of the Chernobyl reactor caused a small amount of dust directly. It caused the displacement of millions of people in that area of the Soviet Union. It was really led about by some reactor design flaws in that class of Soviet reactor that don't actually show up in Western reactors and weren't even used in Western reactors at the time. So for example, 3 Mile Island, which was a nuclear disaster here in the US, because of the design of US nuclear reactors, didn't have this kind of catastrophic runaway. But Chernobyl really struck a chord with people and really led to a really almost overnight change in the perception of nuclear power. And I think, so I have also here Fukushima, which I'm sure we remember from about 10 years ago in Japan. And I think, right, the nuclear industry has never really recovered from these, from the press of these nuclear disasters. That's part of it. In more recent times, we've kind of, so we'll show some of the economics later, but these large-scale nuclear reactors have actually typically they're multi-billion-dollar infrastructure projects, so they're very expensive. Because of disasters like this, nobody wants one in their backyard. So if you plan on going to build a nuclear reactor somewhere and you say, I want to put it in Holland, Michigan, we would all stand up and say, please don't put it in Holland, Michigan, put it in somebody else's backyard. So I think there's definitely that type of view of nuclear reactors. People like them as long as they're somewhere else. There's also an economic component. These are which we'll get into a little bit later, but I like to just point out how stark really this plateau of the worldwide nuclear industry is. We're not building new nuclear reactors, and in large part that's due to Chernobyl as well as the economics of it. Let's talk a little bit about coal power. I like, so this I just got from Wikipedia, which is a great source for random information like this. So if you wanted to look up all of the coal power plants in Michigan, Michigan historically has gotten most of our energy from coal. You can see, this is a list, these are all of the coal power plants in Michigan. You can see there aren't that many. If you look here, this is the size of those power plants. I said a little earlier, Holland's power plant is about 150 megawatts. So it would be about the same size as the Erickson power plant in Lansing. Something like this, the Bell River power plant in St. Clair is maybe 10 times the size. So that's a big one. The Monroe power plant here at 20 times the size, that at the time it was built was one of the largest power plants in the world. Just to give a little bit of a scale for how big these are. So you can see there aren't that many coal power plants currently in Michigan. And if you look at the notes section here on the right, the Bell River plant scheduled for closure in 2030, the DE Karn generating plant 2023 and 2031, it's going to be shut down in stages. The Erickson power plant in Lansing, scheduled for closure before 2023. They're actually in Lansing going to be replacing the Erickson power plant with basically a copy of Holland, Michigan's, of our current natural gas power plant. The Escanaba Power Company, so there's a small one, 50 megawatts, that runs on coal and wood waste. That's not scheduled to close. The plant in Grand Haven, a little bit smaller, but scheduled to close this year. Maybe it already has closed. I'm not exactly sure on that. But you can see basically all of these different coal power plants in Michigan are all either scheduled for closure in the next few years or certainly by 2040. So I think it's interesting to take that into mind. If we zoom out a little bit and we look at former coal power plants in Michigan, there are more former coal power plants than current ones. Most of them tend to be smaller. So we're still running the big, large facilities. But most of these closed in just the last few years. So you're really seeing, right, this chart that I showed earlier where we're switching from coal to other forms of energy. You're seeing this play out in Michigan as well, where we're closing and scheduling to close the coal power plants that are here in Michigan already. And we've closed many of them just in the last few years. Right, here are 4 closures that all happened in 2016, 2019, 2018. Here's our coal power plant from Holland, the James DeYoung power plant, which was a 63 megawatt that closed in 2016. If we look at Holland specifically, I think you get a little bit better sense of why this is happening. So this is the new Holland Energy Park. I take students during at least when we have normal school, we'll see what happens this year, but I take students of tours on the Holland Energy Park, and we actually get to go down on the plant floor and see the operation of the power plant. It's really pretty impressive. When this was opened, and still, so this opened in 2018, it's one of the most efficient, so it's one of the most efficient power plants in all of North America. So it really is, I think we as a community in Holland can be really proud of this in terms of what it's done. It's really kind of led natural gas power here in the US. So as I said, Lansing is considering building a natural gas power plant, and they're basically going to be copying and pasting the design for the Holland Energy Park. When this switch was made from the James DeYoung coal plant to the new natural gas plant, the natural gas plant was about a $200 million project. It's twice as efficient as the James DeYoung plant. So the James DeYoung plant was about 30% efficient. So we actually turned 30% of the energy from coal into electricity. The Holland Energy Park is about 60% efficient. So it turns 60% of the energy from natural gas into electricity. So we have a 2 times increase in the efficiency. We went from a power plant that was about 60 megawatts, 63 megawatts, to one that's 145. But with that, the total amount of carbon dioxide that we're emitting is less than half of the James DeYoung plant. So the James DeYoung plant emitted twice as much carbon dioxide as our current plant, despite the fact that it only made half as much electricity. So that's just one emission. So if you look at other types of emissions, we emit for like nitrogen oxide and sulfur dioxide, we're probably less than a thousandth as much of those types of emissions as the James DeYoung plant. So coal, especially with climate change, people talk a lot about carbon dioxide emissions. Those are important. We'll talk a little bit about them later. But a lot of these other kinds of emissions the switch from natural gas helps all of those pretty immensely. Despite the fact that this was a $200 million investment, it actually has kept our residential electric prices in Holland very low. So they're low, significantly lower than the state average, right around 10 cents per kilowatt hour. So we pay less for electricity despite the fact that we have this brand new state-of-the-art power plant. So that's really what's driving the switch. We can keep our electricity prices low and have all of the benefits from lower emissions. We'll talk a little bit more about this later, but I think it's just interesting to note here what this kind of underlying change in the US infrastructure has done to carbon emissions in particular. So we've seen really since 2005, the 2005 to 2008 range was the US's peak in carbon emissions. So we saw that was kind of our peak in energy production and energy use. And as we've switched to more efficient, lower emission energy generation, like natural gas, like wind, like solar, we've started to now drive down our carbon emissions. At this point, it's been sort of in line with what I would say are international targets for emissions. But as you go further and further out, international targets become more and more aggressive. So I think this will take, to actually stick with international targets and meet international targets, we have a lot more work to do. But I think it's encouraging that we've actually done some of that work already. All right, so that's kind of a high level overview. We'll get into the nitty gritty a little bit of some actual things that are happening worldwide, as well as the cost of some of these things. But before we do, I think, so Josie Sorrell, one of my research students, is gonna try to connect all of, or at least some of these things and show a little bit why, right, as I said before, energy is kind of a challenging subject because in a lot of ways, we as the end users, we flip a light switch and the lights come on. And it's not, if the entire energy infrastructure changed, we would still flip a switch and the lights would go on. So it's challenging because there's not a lot of direct benefit to us. The electricity that comes out of our wall, no matter how it was generated, no matter where it was generated, is still, it's the same for us. But I think there's, if you think about it more broadly and all of the impacts of energy, I think there's a big point to be made that it really is the #1 challenge that we as humanity are facing over the next 50 years, at least from a technical standpoint. So Josie is going to take over and connect some of these things together.
Yeah, so of the list of 10 grand challenges Dr. Christians had up there, I just wanted to choose a few to talk about. And as he said, it's not necessarily like intuitive to think about energy as the biggest grand challenge to solve some of these other issues, but clean, cheap energy can be part of the solution. So I wanted to put the importance of that into context of some of these bigger issues. Dr. Christians, next slide. So I first wanted to start with poverty and standard of living. So the American middle class lifestyle that a lot of us are used to demands a large amount of energy between running our cars, powering appliances, temperature controlling our homes, and all that sort of thing. Those who are in poverty don't have access to or can't afford the same amount of energy to sustain this type of lifestyle. And this plot from Exxon kind of shows that relationship. So they're comparing the Human Development Index of certain countries, which is a measure of standard of living, and energy use per capita. So the light blue section in the upper right there shows wealthy developed countries such as the United States, and they point out Spain and Iceland in there. And those countries are high on the Human Development Index and also very high in energy use per capita. The lower left section, on the other hand, in red there, is developing countries that have both a lower standard of living and a low energy use. And there's not any countries on this plot that have a high human development index or standard of living and a low energy demand, which kind of shows us that access to energy is a huge factor in determining the standard of living for people around the world. So this graphic kind of shows more specifically the relationship between the energy demand of the poor and the wealthy, and gives an idea of just the sheer scale of energy growth that's needed if we're going to bring the poor up to a middle class lifestyle. So that blue bar on the right there is the energy consumption of a refrigerator, and the other orange bars there are the energy use of citizens of 6 different African countries. And as you can see there, a refrigerator on its own uses more energy than a person in all of these countries. So if we want to uplift the lower class, both in our own communities and around the world, to a better standard of living, we're going to have to make inexpensive energy available to them, because a refrigerator is just one appliance in the context of our lifestyle. So this is going to require a huge increase in global energy usage, and it'll have to be inexpensive. So the next thing is food and water security. So right now there are billions of people around the world who don't have access to clean water for drinking, bathing, and farming. So Earth has an abundant water supply in its oceans, and so one of the ideas for solving this problem is desalination. But right now that process is too expensive and energy intensive to be a viable solution for most communities with a water issue. So with a decrease in cost and increase in energy production, this could become a solution for this problem. The other thing is agriculture and food production, which demands a lot of energy between fertilizing, running machinery, harvesting, and everything along this food distribution graphic I have here with shipping and transportation and all of that. So clean and cheap energy could help make this production chain more efficient and reduce the cost, making food more accessible to more people. So the next thing is public health, which of course we're all worried about right now. So first things first, the world population is anticipated to increase up to 10 billion by 2050. This graph here is a world population projection, and it hits 10 billion right around 2050, with the potential following that middle bold line there to reach almost 12 million by 2100. And energy is needed to sustain the lifestyles of all of these people, particularly if we want to uplift the lower class to a middle class lifestyle. And cheap energy is also needed to keep people healthy in general, to run hospitals, deliver resources, manufacture equipment, medications, and all those sorts of things. The other thing is that clean and renewable energy sources in lieu of fossil fuels like coal and oil can improve overall health. Oil in particular pollutes air and water and can cause health issues such as asthma and increased risk of cancer. So this graphic kind of gives an idea of the health impacts of different energy sources. I specifically want to point out the air pollutants bubble, which is the kind of pinkish one in the upper left there, which includes carbon dioxide, nitrous oxides, and sulfur oxides, which are all released when oil and coal are burned for fuel. Carbon dioxide is one of the things that leads to climate change, which we'll touch on a little bit later. And nitrous and sulfurous oxides are damaging to the pulmonary and cardiovascular systems. But then if you can see some of the more renewable sources in the blue bubble up there, like solar and wind, those are less likely to cause health issues. But the other thing that's nice about this chart is that it highlights the interconnectivity between energy, health concerns, and environmental concerns. And if you look, pretty much every single energy source somehow impacts us in the environment. So switching to renewable energy won't completely eliminate impacts, which is impossible to do with the sheer scale of energy production, but can definitely mitigate the risks involved to us in the environment. The next topic is human rights. I wanted to touch on environmental justice a little bit, which the EPA defines as essentially the fair treatment of everyone with respect to environmental policy. And poor and colored communities are much more likely to be located near landfills, bus stations, and factories, which are causing pollution and contamination. And a lot of those burdens of that pollution can be lead-contaminated water, poisoned soil, and air pollution. And this in turn increases their risk of health issues. This graphic on the right there, I wanted to point out Detroit, Michigan, which is fairly close to home. That zip code highlighted is an over 80% Black community and is the most polluted zip code in the entire state. And this pattern continues throughout a lot of the country. So switching to clean, renewable energy sources could help alleviate some of the stress on these communities. The next thing is war and terrorism. I'm not going to spend too much time on this, but I wanted to point out that the majority of US oil is imported, and a large fraction of that is from the Middle East, which can leave us open to political and economic attacks. Just taking a peek at this graph right here, our oil consumption is much, much higher than our domestic production. So we need to rely on other countries to get our energy from oil at the moment. So national security can actually be improved through clean energy that we can produce domestically, because that'll reduce the need to import energy and also slow the depletion of our domestic resources. Through renewable energy within our borders and being able to transport it, North America actually has the potential to become entirely energy self-sufficient. We have plenty of wind and solar resources available within our own borders, and nobody's going to go to war over access to sunlight like they will for oil. So we're going to come back to climate change here. So I wanted to start a little bit closer to home in Muskegon, looking at August temperatures over the past 100 years or so. This graph starts at 1895. So as you can see, there's variation from year to year with our August temperatures, but there's not a clear trend of increasing temperature. However, when you zoom out a little bit more to annual temperatures, you can see there's starting to be an increase starting around 1977, 1978. And our temperatures are definitely more consistently above average as well. There's very few recent years that were below average. And if we zoom out even more to US annual temperatures, the upward trend is even more clear. Yeah, temperatures have been increasing pretty steadily over the past few years. So we're going to look globally now. So one of the common arguments against climate change is variations in solar radiation. So this is accounted for on this plot here. The top graph shows sun energy fluctuations since 1880, and it does cycle. However, there's not an upward trend in solar energy like we would expect if that were the cause for the increase in global temperature. The next two graphs show rising sea level and rising average global temperature, and both have been increasing dramatically over the past several years. And this point right here is 1978, which is the last year with below average temperatures. So the NRDC put together this graphic alongside their clean energy report, showing that with major changes to our energy sources and usage, we can transition to using mostly renewables, reduce greenhouse gas emissions by 80%, and reduce fossil fuel usage by 70%, improving health concerns, mitigating the effects of climate change, and making energy more widely available. Now, this is obviously put together by a very left-wing group, so we're going to dig into some of the economics of energy and see whether this transition to clean energy is feasible.
Okay, so hi, I'm Liz. I'm going to talk a little bit more about the economics, as Jesse said. So obviously energy is a big issue. I think that we've kind of driven that home by now. If we want renewable energy, we have to understand the need and like the scale of the problem. So here we have kind of like a scale representation on the screen. So if you can see in 2015, the global energy demand was 19 terawatts, which is the size of the red circle. That amount of power is like running 2.5 microwaves per person day and night for a whole year. So that's a lot of power. So then from the 2015 data, it is estimated that in 2040, the global energy demand will rise to 24 terawatts, which you can see in the green circle behind that. So now that we know how much energy we need, how can we supply this amount of power? So there was a company that estimated the amount of total attainable power on the Earth. So this is reasonable. We have here looking purely at renewables. If we are able to harness the total attainable power on Earth, we would be able to get 12 terawatts of geothermal. So then from that same estimation, we are able to get 4 terawatts of wind, 2 terawatts of tidal, about 1/2 of a terawatt of hydroelectric. And then the big one, 120 terawatts of solar, and that's 0.1 of incidence. So that would mean that if we were to able to capture 0.1% of the Earth's exposure to sunlight, then we could get 120 terawatts of solar. So the more power of solar strikes the Earth in 1 hour, than we are able to even use in 1 year. So now that we know how much solar we can harness, let's look at the photovoltaic. I'm going to be using PV as a abbreviation for that. So when I say PV, I mean photovoltaic, which is like solar panels. So the PV power potential across the globe. Solar is reasonably well distributed globally. While some areas are better than others, the distribution is still much better than coal, oil, gas, and uranium. So this graph shows the correlation of GDP per capita and insolation. So, which is kilowatts per hour per meter squared per day, which is that y-axis there. And then as you can see, the poorer countries have more access to solar energy, which is kind of encouraging because what Josie was talking about, how there's basically a direct correlation between how much energy people use and how much quality of life and how much money they make as a country. So that's really encouraging that the more impoverished countries have low access to energy supply, if we are able to make solar energy more attainable to these countries, they could probably increase their standard of living. And then before we move on from this graph, I just want to point out Germany on here. We're going to come back to that. So they have a relatively low, almost the lowest ability to produce energy from solar. And just keep that in mind as we move on further, because we'll talk about that. So another big potential is wind power. So many places with solar resources have better wind resources, especially offshore wind. Currently, it's more expensive than offshore wind, but we could take advantage of oil companies' experience with floating platforms. So using things like oil rigs that are already in the oceans and putting some wind power on there. Okay, so to fully understand solar and wind energy, we have some timelines. Some of the initial discoveries in solar here is what we have occurred in the 1800s. The true growth of this industry actually began in the 1950s when silicon solar cells were invented. This is most important to us because the solar panels or photovoltaics that you see on houses and things like that are silicon solar cells. Those are currently the most efficient. But then most recently, there's been a lot of research into different forms of PVs that drive down cost. There have even been developments of solar cells that can be printed like newspaper, which is actually what Dr. Christian's research team is working on right now. So as far as wind energy goes, the first time wind power was used for some kind of energy was in around 1890 when it was used to pump water and gain electricity from that. The most important thing for wind power and honestly any renewable today is in the 1970s, there was gas prices were skyrocketed. Obviously, I was not alive back then, but I'm sure a lot of you remember that. So that was actually a big drive in this whole idea of renewable energy, is because economically, like I'm going to talk about soon, it just wasn't plausible to use gas. This led to many advancements. And then the coolest stat, I think, is that in 2018, the total installed capacity of these wind turbines that you see when you're driving down the road, they actually had enough power to produce electricity for 28 million homes, which is a lot. So back to this graph that Dr. Christians had earlier, these advances in technology coupled with the driving down of costs, like I talked about with more research, has led the US to retiring coal, natural gas, and nuclear. So as you can see in this graph that just popped up over there are here the net additions to the renewables has grown greatly in a few short years. So the more we talk about the economic advantages to renewables, the more we need to know the unsubsidized costs of these different types of energy. So Lazard is a financial advisory and assessment company that has put this graphic together. So you can see that on the x-axis, we are able to see like the levelized cost, which it's in cost per megawatt hour. And to put this into perspective, that average energy company usually costs about 12 cents per kilowatt. So on this graph, that would be $120. So as you can see, the line that we have put in there, that's around 12 and a half, 13 for the levelized cost. So that's basically what we're paying right now. As you can see though, most of the renewables, so in the section that says renewable energy, you can see wind and geothermal and solar, those are much cheaper and not around the cost that we are even paying now. And then you can see that kind of the reason why these nuclear and coal are shutting down, because they're simply more expensive. They're just lying along the lines of what we have today instead of these lower cost alternatives of PVs and wind. So here's a look at different types of energy resources and their levelized costs from the same company that we had before. So this is since 2009. So we have right here, coal is actually down in cost 2%, even though it looks pretty stagnant on here. Nuclear is up by 26%. Natural gas is down by 32%. Wind is down by 70%. And the really cool one, I think, is that solar in this graph is down by 89%. It's just wild to me that this is since 2009, and in just 10 years, we are down by 89%. So the funding that was poured into wind and solar now, you can show it's showing a great return on investment with these new technologies that are actually really paying for themselves. So in a little bit of a transition here, with the falling costs of renewables, many different countries have been able to use their resources to develop their energy plans over the years. That being said, energy generation will continue to diversify. In the economic breakdown, we saw how cheap clean energy is. This will eventually lead to more use of wind and solar, not only because of cost, but also because of their abundance. So we're going to talk about some unique resources that different countries have and how they've really tapped into these natural resources that they have. So Canada and Iceland, we're going to talk about those. So here's a breakdown of the energy use in Canada. This is close to home for us, we could drive right there right now if we wanted to. One place that is with Canada, it has a large amount of water access. So actually 59% of their energy comes from hydroelectricity. Actually, when we were talking about this creating this presentation. Dr. Christians mentioned that he has some family that's from Canada, and they actually call power lines hydros because that's where they get their energy from. They're also the second largest hydroelectricity producer behind China, and their installed capacity, they're able to produce 85,000 megawatts of energy from hydroelectricity. So much like Canada, Iceland plays into their abundant resource of geothermal power. Geothermal accounts for about 65% of all energy production and about 85% of the total primary energy supply is renewable. So Iceland is the world's largest green energy producer per capita and largest electricity producer per capita, with approximately 55,000 kilowatt hours per person per year. In comparison, the EU average is less than 6,000 kilowatt hours. So they're using a lot of energy, but they also have a master plan to go 100% renewable. So like I said earlier, we're gonna look back at Germany here. So if you guys can remember back to that graph, Germany had very little access to solar. They don't really have offshore wind. So it's not a country that you would think, not like Iceland or Canada, where they have this abundant resource. So if you can recall, Germany has some of the worst, actually the worst solar potential in the world from a resource standpoint. The north of Germany has about the same amount of solar resource as Fairbanks, Alaska. But in 2013, Germany invested about $458 million into a renewable energy resource in response to their, I'm going to totally butcher this because I'm not good at German, but it's called the Energy Energiewende. Yeah, so I'm not good at German, but that's what that translates to is the energy flip, the energy turnaround. They wanted to go from being something that was predominantly relying on coal, and then as you can see from this data in 2019, they actually have now 47.3% of their energy production is renewable resources. So even though Germany has a lower level of solar exposure, they were the world's largest installed PV capacity in 2013, which is kind of crazy because they don't get much solar. But in 2018, it was also estimated that they had around 338,000 jobs in the renewable energy sector of Germany. So not only are they pushing towards more clean energy, which can become more efficient, but they're also creating a ton of jobs in their goal to be 100% renewable. So I'm gonna pass it back to Dr. Christians.
All right, thank you, Liz. Yeah, so hopefully we've convinced you that energy is not going to be a one-size-fits-all solution, especially the transition to clean energy. You'll have places like Canada and Iceland that can take advantage of their unique geography or their unique access to specific renewable sources. And then you have countries like Germany that are going to have to do a little bit of everything in order to continue to expand their access to renewable energy. But even a country like Germany that has relatively poor access to renewable energy, as you can see, they're at about 50% renewables, despite the fact that they have pretty terrible renewable resources. So I'm going to talk a little bit about the US and what does renewable energy look like the US and why I think we're positioned to be a leader globally in the transition to clean energy. Currently, we use about 20%, I think 19% of global energy is the latest data, which is crazy to me because we are a country of 340 million people. I forget the exact number, but we use 20% of all the energy in the world. So we are a country that uses significantly more than our fair share by population. We're currently about tied with China. I think in the last couple of years, China pulled a little bit ahead of us. So they maybe use 21% of the world's energy and we use 19, something like that. But I think our leadership in energy technology, because of our global position, our leadership will have worldwide consequences. That's including like driving down costs. If we drive down the cost for, say, renewable technologies, a lot of the developing world, instead of going through, instead of first investing into coal, oil, natural gas, which maybe they don't have good access to, they'll instead be able to kind of skip that phase of industrialization and go straight to renewable technologies and have more abundant and cheaper access to energy. The U.S. is also interesting because we have we're a big country. So unlike, say, Iceland, for example, we have a big mix of different geographic areas. So it makes for an interesting global case study because there's actually a lot of, we use a lot of energy, but there's also a lot of different types of possibilities that we can take in order to make that energy. One thing that I think is just good to keep into perspective when talking about solar. So Liz showed those circles that show kind of the size of energy we use. We get as much energy from the sun in 1 hour as we use in an entire year, which is, I think, a little bit mind-boggling. But let's assume a worst case, or what I'll call a worst case scenario, where you know, tomorrow somebody flipped a switch and said you can't make energy from anything else but solar. Right. So if we couldn't make energy from anything else than solar, how much space, how much land area, how many farms would we need to put solar cells on? I think the answer is a little bit surprising. It would be about West Virginia. Right. It wouldn't necessarily be West Virginia. We'd probably put it in a mix of like New Mexico and Arizona and Texas and maybe the Dakotas. But it's actually a relatively small, at least in context, right? We use, that's 20% of the world's energy. It's about 20% of urban land area. So if we can find creative ways to install solar in already urbanized land, right? In cities, on rooftops, over parking lots, if you can find creative ways to install solar into urbanized land, like on people's homes, that actually can make up a fairly large fraction. So we don't need that much in other locations. And I think this is kind of a surprising stat. That's actually less area, right? We put, well, back in the day, we put lead in gasoline to prevent knocking. We don't put lead in gasoline anymore because there are a lot of health hazards with lead pollution. So instead we put ethanol in gasoline. We get that ethanol from corn. We make corn ethanol. We actually, in our intro to engineering class, we have a lab where we get to make corn ethanol, which is pretty fun. But we make ethanol from corn. We put that in our gasoline. The land area that we use for growing that corn is about actually a little bit more than the land area that we would need to go to 100% solar energy. And this plays out too on a global scale. So if we looked at global energy, these 6 red squares are each about 100 kilometers on a side. They're all placed in deserts in different places, right? In the Sahara, in the Middle East, in Mongolia, in the middle of Australia. These are obviously just placed in areas of high solar insolation. But if we, right, this is kind of a thought experiment, but if we made those each really big solar cells, that solves that covers all of the world's energy. So they're obviously very large areas, but they're not impossibly large areas. So we can transition to large fractions of solar energy. We don't need to go to 100%. We're going to be, you know, there are places like Canada and Iceland that have really good hydroelectric or geothermal resources. There are places that have really good wind resources. But just to give a sense of the scale of what type of land area that would need. Some of the kind of interesting things that are happening more recently is people look at that, that land area and say, well, maybe there are some interesting ways that we can use that and kind of make dual functional things where we can make, we can harvest solar energy in ways that aren't just putting a whole bunch of solar panels in a field and taking up that space? Can we use things as kind of dual purpose? So some of the research that I'm working on with Liz and Josie is looking at different ways that we can do this. We can make new technologies that don't currently exist. These are all different ways of using solar energy that are kind of currently, I would say, in the prototyping and product development stage. So there are semi-commercial technologies right now, but basically we're trying to think of, are there different ways, right? Putting solar in windows, putting colorful solar cells in things so we can actually make it an architectural feature. Doing things like integrating solar into greenhouses, large roof spaces that already exist. Can we integrate them into bus stops and skylights, into roof shingles directly? So I think that's one of the things that will continue to happen is not only will we get more diverse generation from, say, solar and wind and geothermal and hydroelectric and all of these other sources, but the ways that we're actually harvesting this will be able to get more creative as we start to drive the costs down of these things. And they'll be able to be more integrated into modern life instead of just being a whole bunch of panels out in a field taking up space. We can actually kind of take them and use them in different products and in creative ways. One of the things that we do have to think about, especially, solar energy, wind energy are fairly easy as long as we don't have a lot of them. We can kind of, right, when the sun's not shining, we can make up the difference with, say, natural gas. So we do that already, and right, the energy is bought and sold kind of like the stock market. So if it's really windy in Indiana, the power plant in Holland says, well, it's not worth it for us to burn natural gas and create power, so we ramp down our power production and we buy wind energy from Indiana. That's already happening. If there's not this base load, or what we call a base load in the energy industry of fossil fuels, of things that you can turn on and shut off, if we're using more variable power, like solar, like wind, storage becomes a more major component, something that we have to think about. Two different possible technologies. One is batteries. Batteries have continued to make really surprising and promising gains. So this is for batteries for cars. If you bought a Toyota Prius in 2009, the price that you paid for the lithium-ion battery in that Toyota Prius, that cost has come down by about 85% or 87%. In just the last 10 years. So that's why you're starting to see cars like Teslas, which in 2010 maybe cost $200,000, now they cost $35,000. It's really driven by a reduction in the cost of batteries. And that's why you're starting to see automakers like Ford and GM and Toyota really start to invest in electric cars. It's because those battery prices are really dropping pretty rapidly. So batteries are one possible way. One kind of off-the-shelf, or what I'll call off-the-shelf method for large-scale storage is what we call pumped hydro. So pumped hydro is basically the idea that we could build a hydroelectric dam. We already know how to do that. We've been building large-scale hydroelectric dams since the Great Depression, right? That's when we built the Hoover Dam. But we don't necessarily need to build it on a river. So this picture here in the bottom, this is Presenzano, in Italy. And it has two lakes. So there's a lake at the bottom of the mountain and there's a little lake at the top of the mountain. And there's a hydroelectric dam, there are hydroelectric turbines in between those lakes. So when energy is available, say the sun is shining, we pump water up the hill. When we need energy at night or when it's cloudy, we let the water flow back down the hill and we use it like a hydroelectric dam. So it's basically a reversible hydroelectric dam. This is already a well-established technology. We actually, if any of you have been to Ludington, some of the early days of pumped hydro storage were coupled with nuclear power. So there's a nuclear power plant near Ludington. And near that in the 70s, they built what at the time was the largest pumped hydro storage facility in the world. I think currently it's about number 5. So about the 5th largest pumped hydro facility. It's right on the shores of Lake Michigan. So they built it for a nuclear power plant because nuclear power plants you want running basically at 100% all the time. So no matter what electricity demand is, you want to be running your power plant at full capacity. So when demand goes down, and normally you would turn your power plant down, instead we just use that electricity to pump water from Lake Michigan up into a reservoir up on the sand dunes. And then when we need that extra power, we can let it flow back down. That system in Ludington, I believe, is about 1,700 megawatts. So it's about 12 times the size of our current Holland power plant, just to give you kind of a sense of the scale of some of these systems. This system that you're seeing here in the picture in Presenzano in Italy is a closed loop system. There's a 500-meter elevation difference, which is about a 1,600-foot elevation difference. So it's a fairly large elevation difference, but this system with those relatively small reservoirs is about a 1 gigawatt. That'd be 1,000 megawatts, which is enough, right? That's roughly 6 or 7 times the size of our Holland power plant, just to give you a sense of the scale of these systems. So they don't actually need to be very large in order to have that kind of power output. This is a study done by a group at the University of New South Wales in Australia, where they looked at, they used Google Earth and mapped out possible locations for pumped hydro storage. They made sure that none were in cities or national parks or anywhere close to cities or national parks. And they found that without too much work, you can get about 100 times more locations than are necessary for this kind of storage. So this is basically an off-the-shelf technology that could be coupled with renewables to make storage possible. It doesn't add that much to the cost of some of these some of this electricity. One of the other things that will need to happen, that's starting to happen but isn't quite there yet, is large-scale transmission. So what we need to be able to do, and this is really one of the technical challenges that still lies in front of really large-scale, what we would say as high penetration. If you wanted to do 70% renewables, for example, you need to be able to take the electricity from where it's produced, where it's sunny, and move it to where it's cloudy. We've already demonstrated there's a number of large-scale transmission lines, big electrical lines around the world. One of the largest is in China, and this is that electric power, this transmission line mapped onto the U.S. So this is technology, again, that already exists. We can transport electricity with relatively low losses on the order of 3,000 kilometers. So we could, in theory, if we set up an infrastructure like this, we could take electricity from the deserts of Arizona and take that all the way to New York City. Being able to have a flexible grid like this, where you can take electricity from one part of the country and move it to where it's needed, this is really going to be important as we for managing variable renewable sources. Because, right, if it's sunny in Arizona and it's cloudy in New York, you can take that energy and move it to where it's needed. If it's windy in the Great Plains, but it's cloudy in Michigan, you can take that energy from the Great Plains, from those wind farms, and transport it to Michigan. So you're setting up almost what would be, right, like a little bit analogous to the oil pipelines that we're used to, where we're taking energy from where we're harvesting it, where we're pumping it out of the ground, and we're moving it to where we can actually use that. So this is technology that the technology side of things exists. The cost isn't prohibitive. Some of these have actually been built, but it's definitely one of the things that will need to happen in order to make large-scale renewables happen here in the US and elsewhere. So let's give a little bit of a case study to see kind of on the ground what is actually happening and what are utility companies doing, because they're actually a really key player in the transition from energy, because these are the people that make money on this, right? They're they're the people that if they can drop their operating costs and keep charging you the same fee for your electricity, then they make more money. So that's what they're going to do. If they're going to make a change and that increases their operating cost, you don't want to pay more money for your electricity, so they're not going to do that. So this is an electric company, Xcel Energy. Maybe you've heard of them. They're one of the larger electric companies in the United States, or the electric utilities. I first came into contact with Xcel Energy because they were my electric utility when I lived in Denver. They have about 3 million electricity customers across 8 states. So in 2018, they were looking, there's a coal power generating station. It's actually the largest generating station on their, in their customer base, in their grid. And they announced plans to shut down 2 units of it, which together were about 1,000 megawatts. So again, like 6 or 7 times as big as the Holland power plant. So a fairly substantial amount of electricity. And what they did is they said, we're going to be technology agnostic, right? We want to make the most money that we can, so give us your best price. We don't care what it is. We don't care where that electricity is coming from. We want that to be the cheapest possible. So they solicited open bids to replace that, about 700 to 1,000 megawatts, in an all-source solicitation. And their plans, this is a little bit important. So some of the financial things that Liz was showing you are for 2019. Xcel, when they did this 2 years ago, their plans were for a new system to come online in 2023. So it's a little bit different because companies are kind of projecting out what their 2023 costs are going to be. So they're kind of pricing in future cost reductions a little bit into their bids. But if we look at what bids actually came in for Xcel, it's pretty surprising. So they got around 430 total bids, which you can see here at the bottom, for 238 different projects. So there's a lot of different bids. A lot of companies are bidding, some multiple times, but there's a lot of data here for somebody like me. And one of the surprising things that people noticed, basically, as soon as Xcel shared some of this information, is that renewables, wind and solar, were just the cheapest of any different energy that they were bid. So they were cheaper than gas, they were cheaper than new coal, they were cheaper than anything else. So that was a little bit surprising, not too surprising, because right, if you think of where Xcel Energy is, it's in the Great Plains, it's in Colorado. Those are kind of uniquely good places in the US for both wind and solar. There's a lot of sunshine, there's a lot of wind. So this is in some way kind of a uniquely good place in the US for these technologies. But if you remember the costs a little bit that Liz was talking about, right, in 2010, solar was about $350 per megawatt hour. Now the prices that Xcel is being quoted for solar are around $30 per megawatt hour. So more than a 90% reduction. And actually solar with storage, so they're basically coupling a system of solar cells with batteries, are still only around $36 per megawatt hour. So this is now cheaper than what natural gas production would be. So we're starting to see where coupling renewables with some sort of storage system is actually becoming cheaper than fossil fuels. And it's really surprising if you look at wind. Wind, this is the median bid price. So they're actually priced, right, significant number of bids lower than this. The bids were coming in around $18 per megawatt hour. If you remember back to what Liz was saying, the LCOE for natural gas is maybe $60 per megawatt hour in the US. So now we're coming in with projects like wind. This is wind and battery storage, still significantly at $21 per megawatt hour, significantly undercutting fossil fuels. So this is happening already in places in the United States where it's becoming it's becoming good business sense to start replacing some of your fossil fuels with renewables, particularly wind and solar. So you can see that on Excel's mix of energy. In 2005, about 20% of their energy was what they call carbon free. So most of that, about 10%, 12% was nuclear. The rest were solar, wind, and hydro, but basically hydroelectric. By 2013, this dark green is the growth of wind. So I said, right, Excel is in the Great Plains. So when you drive out to Colorado, you drive past a lot of wind turbines. This is what you're seeing. You're seeing a growth from 2013 to more recent of really a dramatic growth in the amount of wind energy that Excel is using. Again, because that's the cheapest form of energy. It's cost effective for them to be decreasing the amount of coal and increasing the amount of wind. If you look at Excel's future plans, again, these are people that this is how they make their money. They also have a little bit of a public image thing, but primarily this is because this is how they're going to make their money, and they also want to play it up a little bit. Their 2019, their carbon emissions were almost half of what they were in 2005 because of this switch to wind. Their goal is to get to an 80% reduction by 2030 and 100% reduction by 2050. So this is their future plans. They're the first utility in the US to be able to commit to 100% carbon-free electricity production. But I think it's kind of surprising how fast some of these changes have happened, right? In 2005, only 20% of their electricity was carbon-free. So because of the really rapid drops in cost over the last decade, basically if your economics are stuck in 2005, you're way behind the times. The economics have changed just completely on their head. So just to summarize a little bit before we open up things for questions, right, I hope we've convinced you, and we know this from our personal experience, energy use is key to modern life. And really, use has to, especially worldwide, use has to increase as we try to increase standard of living, as we try to lift people out of poverty. The amount of energy that we use is going to increase, and it has to increase. The rapid shift in renewable costs has made it the cheapest option in many locations. But it's not easy, right? Investment that we make now, like we saw before, really we've been making investments since the 70s in some of these technologies, since the oil crisis in the 70s. And this is the time where, right, we've started to see some of these initial investments that were made when renewables were not the cheapest. Those have driven down costs, and now it's becoming, right, we're seeing some of the fruits of those investments play out. As we start to expand capacity, we're continuing to drive down costs. So the investments we make now are paying off for us, and they're also paying off globally. So actually, when Liz was talking about Germany, Germany was early, kind of early to the race for solar. So they started in 2010, 2012, really investing heavily in solar. It wasn't very economical in 2012. Their investment in solar, their large deployment of solar has made it economical for the rest of us. It's expanded companies' capacity, it's driven down costs, it's helped the economics for countries like us to be able to pick that up. And we can help do the same. It's not only beneficial for us as we continue to invest, it will lower our costs, but it also will benefit others, and likewise, we've been benefited by the investments of others. The most recent trends in the US are really a de-investment from the coal sector. I know there's been different talking points politically about exactly why that's happened, but really it's just been cost. Coal is not economical anymore, so utility companies are shutting down coal plants and they're replacing it with natural gas, with wind, and with solar because they can make more money that way. And there's no, given the cost trends of these other technologies like gas and wind and solar, there's kind of, it's increasingly becoming apparent that in most places coal won't make sense and doesn't make sense anymore. There are still some big issues that need to be attacked. We need continent scale transmission to really smooth out variable weather patterns. We need to be able to take energy from where it's being made at that point and be able to transport across the entire continent to where it's needed. That reduces the amount of storage that you actually need. So you don't need 3 months of storage because it's cloudy in Michigan for 3 months during the winter. It's sunny in Arizona. We just need to be able to take that electricity from Arizona and get it to Michigan. We also need, we do need a large amount of storage. There's continuing a reduction in cost of battery storage. I think pumped hydro storage is already a proven technology that's already on the grid. We already use about 98% of the storage that we use currently is pumped hydro. So with some kind of creative ways of using that, we do need storage, but I think hopefully if we can get transmission and storage coupled together, we can still kind of, right, what we want is we still want to be able to flip the light switch and have the lights come on. But I think there are going to be a lot of changes. There are a lot of changes happening now, which hopefully can help us do that and do that in a way that's less expensive or the same cost for us, the end user, but has a lot of these benefits for people in the developing world, for people in poor areas here in the US and throughout the world. So I'd love to answer any questions. I really am just so appreciative of the time that you guys have all given me and my students. We're happy to take any questions at this time now.
I have one for you, actually, Dr. Christian.
Yeah.
I would think that one of the things that would be different about renewables is a different cost percentage operating versus capital. I would think that once you've got the solar panel out there, it needs hardly any maintenance.
Yep.
Will last much longer than, say, a coal-fired boiler. How does to what extent is this the case, and how does it play into the economics that you discussed?
Yeah, absolutely. Great question. Yeah, so you're right. The economics are different because you're right. If you're building a coal power plant, you have this ongoing fuel cost. So you have typically for something like coal or natural gas, your ongoing fuel cost is the major cost that you're paying for. For solar, the major cost that you're paying for, most all of the costs that you're paying for, aside from some small costs for maintenance and upkeep, is that initial installation. So what that means for renewables, durability of that product is actually, it becomes almost the key aspect to the cost. So you need to be able to, so for current solar cells, for example, they have about a 25-year warranty. If you can stretch that out, if you can make them more durable and last for, say, 30 or 40 or 50 years, you have the same initial upfront cost, but now you're getting energy for more years. So that's really one of the key, it kind of changes how you try to reduce the cost of the technology. And for solar, it's really pushing on stability, on how long those things will last is really a key component. But yeah, it definitely, the economics of things change from a utility standpoint too, because utilities are now, like if people are putting solar on their house, or say like a university is, it changes, who's actually doing the generating, where utilities are used to generating and then selling it to everybody else. And then now people are generating and the utilities are acting as kind of the distribution network and the middleman and like a little bit of the backup. So there are definitely, there are a lot of things that still need to be worked out. But that's a great question.
Hey, Dr. Christians, a lot of questions are in the chat section. I know you can't see that right now because you're presenting. I just wanted to let you know.
Okay, thank you. Do you want to pick out one, Liz, and then read it?
Yeah. So let's see.
Here, let me or I can stop sharing and then.
Yeah, I don't think you're gonna need any of our slides, so I think you'll be good.
Okay. So here's one. What are the biggest changes we could make in food production consumption to save energy? I think the biggest change, so food production, if you look at where emissions are from, I'm going to get this wrong, but it's at least ballpark right, and it's easier to remember. It's about 25% from food, about 25% from industry, about 25% from electricity, and it's about 25% from transportation, like cars and airplanes and things. So food production is actually a big fraction of the emissions that we have, and it's probably the hardest to do anything about. I think switching diets from meat to more like a vegetarian diet or more like an Asian diet has something. I'm not an expert in that, but I know it's definitely something that's interesting. Here's one from Ken Freestone. Where will we be getting most of our solar supplies and equipment in the near future? The US, China, other? So right now it's from China. So starting in about 2012, China really invested in their domestic production of solar and really kind of took over the market. So if you remember the collapse, this is one that maybe some of you will remember, is Solyndra, which was a California US company that the government had invested in, and they had a business model that was going to make them successful. And really what happened is China invested more heavily, undercut the prices of Solyndra, and Solyndra said, we can't make things for that price. And they went belly up, and it was, I think, like $100 million or something loss for the government. Really, since that time, China has taken most of the production. There's one major company in the US which is responsible for something in the ballpark of like 5% of world solar. There are new technologies which are out there that the US is now investing in to try to basically shift the market from silicon and hopefully bring some of that production here to the US. But currently it's mostly in China. Are you able to discuss the capability of the grid to handle intermittent resources? And do the Lazard numbers consider the full cost? So the Lazard numbers, I would say the levelized cost of electricity, those numbers, they reflect that it's an imperfect measure. So it does not reflect the full cost that it would take to go 100% renewable. And that's because there are kind of diminishing returns. Basically, we need energy all the time, but if you installed all solar, you get most of your energy when the sun is shining and you don't get any energy at night. So you need to have extra costs in things like storage to be able to offload that demand. There are also, other ways that you could change the demand so that you could basically take more of the electricity that we use at night and shift it to the daytime, potentially with some things like that. But it definitely, after you get above about 20% of all of your power from renewables, you start to have periods where you're getting more production from renewables than you actually use. So that's already happening in Germany and California, where they're starting to get periods in the day where maybe you see a news article about it. California has 100% of their electricity from renewables. And that happens already. But really what that means is if they put more solar on the grid, so that on average they're say 25% or 30%, they'll have periods of the day where they have to turn down their generation in order to keep the grid stable. That can happen actually fairly easily with solar, a lot easier than oil and gas, than like ramping up or ramping down production in those. But it's definitely more challenging. So from a grid stability issue, Hawaii in the US is probably leading the way in terms of trying to plan out how that will look. But it's not easy. It's a big and challenging problem for sure. Okay. How do subsidies for oil and gas compare with renewable subsidies? I'm not 100% sure on the most recent numbers for those. The costs from Lazard do not reflect subsidies, and a lot of the subsidies that have happened, a lot of the most aggressive subsidies have started to phase out. But the costs that we showed were not reflecting subsidies, but they're also not reflecting, if you wanted to, say, invest completely in that technology, then the cost would, kind of the marginal cost would change. An observation, many times when we say, oh, there is plenty of blank, we find that later we create a problem. That's absolutely right. I think one of the things that we really have to take into consideration, so energy is an unbelievably large industry worldwide, right? This is, as Josie showed in one of her slides, it's really tied to, tied pretty directly to standard of living in what we think of as a developed country, right? There are no third world countries that have lots of energy, and there are no developed countries that don't have energy. That doesn't happen. But I think if we're talking about hopefully the shift from renewables, there have been a lot more studies recently and run by a lot of different groups. So there are, right, stakeholders, people like me that have done studies, but there are also people like ExxonMobil and Shell and BP. If you look at their projections for the future or where they're investing money in, they're investing money in all of these technologies as well. And they're really seeing this type of shift. One of the companies that's in the US here that's investing pretty heavily in development of new solar technologies is Hunt Oil, or it used to be called Hunt Oil. I think it's now called Hunt Energy, because they're rebranding themselves. They're not it's an oil company in Texas, as one of the few private oil companies, or one of the largest private oil companies, and they're changing how they're branding from Hunt Oil to Hunt Energy because they're really seeing, you know, this is the path that things are going in terms of cost, and they're starting to invest more heavily in how can we be the ones to develop some of these new technologies and some of, you know, what's going to be next from this. I apologize if I'm missing questions, but are the large transmission lines privately owned? Does that cause a problem with ease of long distance transmission? So the electrical grid currently in the US, so for example, just again, kind of a local example, our electrical grid that we're attached to in Holland, we have our Holland power plant, but that's actually connected to a grid that stretches all the way from Canada down to Louisiana. And you can think of it a little bit like a municipal water system where, right, everybody's connected to the same water pipes. And there are a whole bunch of water towers on that system, but there's nothing really to say that if we turned off this one water tower, you'd still get water. It would just be from a different water tower down the road. So that's a little bit how our current grid works. But if we try to take electricity that's generated here in Michigan and transport it all the way down to Louisiana, currently we have a lot of losses from that with our current grid. So what I'm talking about is basically trying to make that type of kind of beefing up, I guess, our current electric grid. So it would really be run, in a lot of ways, it would be run the same as we currently run it. But it would give us a little bit more flexibility or right? It's kind of like installing a big water main on your municipal water system. It gives you easier ways to transport that long distances.
I just wanted to let folks know that our class was due to end at 11 o'clock. I, for one, have had such a good time listening to this that completely escaped me. I did want to take this opportunity to thank Dr. Christians for his time. And certainly anybody else who wants to stick around and continue the questions. I think this has been a wonderful session. And I just wanted to jump in and say thank you so much, so that we didn't forget what's really important, which is to recognize your time and, of course, energy, as well as that of your students. And thank you for bringing what you shared with us this morning, Dr. Christians, Liz, and Josie.
Yeah, thank you.
Thank you.
Thank you all so much for being here. I can't believe how many people we had show up. This is fantastic. So many questions. This is great.
It was a full class and we do appreciate it. Are you able to stick around maybe till 11:15, just 5 or 6 more minutes to answer some additional questions?
Absolutely.
Awesome.
Thank you.
Yeah, absolutely. So if anybody has a question that they want to ask, you're free to unmute yourself and we can just chat. Otherwise, I can keep reading some of the questions along here as well.
Can you hear me?
Yeah.
Yeah. My question was related to something I think Josie had mentioned regarding importing oil. I thought we were energy independent in this country now. Is that not the case?
So it's not the case that we are not importing any sources. We're primarily, I think, on an electricity standpoint, we are energy independent, but that's not true for oil and gas, for like automotive transportation. So I believe that's the distinction, is from electricity. I could be getting this wrong. I'm doing this off the top of my head without knowing, but I believe the distinction is for electricity production, we are independent, but not for transportation.
Okay, and one other follow-up to that, or independent of that, the previous question regarding these transmission lines, I didn't catch if in fact they're privately owned or if they're government owned, let's say, or publicly owned.
I think they're typically owned by the utility. But I think one of the things that we're kind of running against, or utilities are really running up against, is they're in some ways having to reimagine their role in the whole system. Especially as people are putting, solar panels on homes and generating their own power, the utility company is then serving as a backup. So how do you actually financially make that work? Because that's obviously a really important part of the system. So for large scale transmission, I'm not sure exactly how that would look. I think that's something that's still a little bit of an open question. Currently, the distribution system, the power lines, everything are utility owned, but it's a little bit of a, it's a challenging thing because there are a lot of stakeholders in there. Obviously, federally, there are the companies individually and the end users, and all of us have a stake in having an electric system that works well.
Right. Well, just overall, I think it was a great presentation and a great job by the students as well. So thank you.
All right, appreciate it. Okay, oh wow, thank you, Dave Coster. So sounds like you have better information than I do on the transmission. Thank you, Dave. So he says, many transmission lines have been divested from vertically integrated utilities from the utilities and are now being run by private companies. He says ITC is the company here in Michigan. Thank you, Dave. I'll have to look more up on that. That's something I'm definitely not very familiar with, but that's some good information. Thank you.
So it seems we have a lull in people jumping in. So this probably is a good time to wrap. Again, thank you for your time, Dr. Christians and Josie and Liz. This will be recorded. It will be posted on the YouTube channel for HASP. And if you have any questions, you can email HASP and we can get back to you on any questions you have regarding this class. So thank you very much, everyone. I'm going to go ahead and stop the recording. Yay.
Thank you.
And thank you, Susan.
Thank you all. Have a good day.